Does the trick.
So our problem here is that what we just did was we compared two groups, right? We looked at male heights and female heights. And our mining example didn't do that. Our mining example compared a group to a mean, to an average. And the average that we compared to was this upper bound of this acceptable range of stress levels. Okay, so what we want to do is we want a different kind of t statistic. And sort of break the mystery now, there's foreshadow a bit and say that there's three different kinds of t statistics that you can deal with. And what you've seen is a t statistic for a one sample t-test. We've only got one sample. And that's different to what we've just done, where we've got two samples. So let's go back to our mine and let's imagine that that the mine has accepted that they've got a stress problem and they want to know who specifically is stressed. So what sort of intervention should they have? My brother works in the mines, he's a mechanic, and Australian mines are very unionised, very strong unions, and the way that it works is that when you start working at the mines you get night shift. So he has a very, very different day rhythm to all of his friends and all of his family, and that could be a contributing factor of stress. So is it the fact that you work on day shift the cause of your stress, rather than the fact that you're a miner? So now we've got a new null hypothesis, and that is that night and day shift workers have the same blood cortisol levels. And we've got a new alternative hypothesis, which is that they have different blood cortisol levels. So if we're talking about this in terms of statistical distributions, what we're really saying is that night and day shift workers come from the same population with the same parameters. That's our null hypothesis, because our hypothesis is always about a distribution with some parameters. Okay? So we're saying that null hypothesis, same population, same parameters, describes everybody. Alternative, different distributions with different parameters to describe night and day. Null hypothesis looks like this. Alternative hypothesis looks like this. Two different distributions. So how do we quantify this difference and how do we test the alternative hypothesis? We use something called an independent samples t statistic. And it looks very different. It looks more daunting, it's got more stuff in it, but the logic is the same. Here we've got the mean of the sample of night miners, and here we've got the mean of the sample of day miners. So what we're looking at here is a difference again, but it's not the difference of the sample to some sort of baseline mean, which was 23 before. Now it's the difference between the two samples, the means of the two samples, the averages of the two samples. So this would be like the averages of the men and women that we saw before. And we're dividing again, not by the standard error, but we're dividing by something that does something similar to the standard error. And I'll just say what that is. That's the square of the pooled variance divided by the number of subjects. And what this does is the same thing as the standard error. I'm not going to go into detail about what it is. Basically, it's just put everything together and take the standard deviation of both samples together. And then divide and square it, and divide that by the number of subjects for group 1, number of subjects for group 2, and take the square root to get back to your distance from the mean. So this does the same sort of thing as what the standard error did before, is it punishes you. So the bigger this is, the smaller your t is going to be. The smaller this is, the bigger your t is going to be. So again, it's the same logic. Difference between sample means divided by some estimation of how well the samples represent the two groups. Other than that, it's the same sort of thing. We get the p-value in the same sort of way. And remember I said at the beginning that we have a difference when we have to approach things slightly differently if there's some sort of structure in the data or there's some sort of similarity between the two groups that we might be interested in. So if we're testing the same person twice, then there's less changing than if we're testing two different people, say for a drug trial. Or what we'll do next is we'll look at different makes of cars. if we're looking at different models versus if we're looking at the same model of cars change over time as it's being developed, we might want to take into account that consistency or some consistencies that we should expect to be there when we measure the same entity twice, or when there's a dependence between things that we're measuring. So we could, for example, imagine a new scenario where we increase pay. So maybe the miners are stressed because they're underpaid. So let's give them a pay raise and then look at the effect of the pay raise on decreasing stress. This is the same group of people before and after a pay raise. Again, we can plot it like this, where the null hypothesis says that there's no effective wage rise, and the alternative hypothesis would look like something like this: less stress after the wage rise. And that has an equation, and that equation is the difference between the two samples. The average difference between the two samples, minus the difference we would have expected due to chance, minus the null hypothesis, divided by the standard error of the differences. And don't worry about the details. The logic, again, is just, now we're not focusing on a sample over here and a sample over here. Now we're focusing on a sample of differences, because we can track one person through time. Whereas before, you can't relate subject 1 in the night miners to subject 1 in the day miners, because they're completely different people. There's no justification to link them in any way. In the men and women sample that we looked at before with heights, you can't link male number 1 and woman number 1 because they're not the same person. But in our salary intervention, Philippa is still Philippa after her salary is increased. And what you're really interested in is how her stress levels change as an effect of that intervention. So what you're watching for is Philippa before and Philippa after. So what you're allowed to do in this case is take Philippa's score and subtract her old score, and then just look at the distribution of differences, divided by some estimation. So that's 3 different t statistics, counted in 3 different ways. Okay? Good?
The t value, is
Yeah.
it, the reason why we want that to be large is because then it's easier to get a significant result.
Practically.
I mean,
Yeah.
in relation
Yeah.
to the punishment. So
Yes, what a large t-value tells us is that if you've got a very large t-value, you've either got a very big difference or you've got very little variability in your estimates. So you can have an incredibly small difference that doesn't matter, but there's so much consistency that it ends up being significant anyway. And that's important because significance doesn't mean importance. So you could have a drug, so you could have an effect, you could have something that very consistently changes people on a parameter or on a variable that they're already very consistent on. It only does it a tiny little bit, and it'll look like it's very significant, but that effect that it causes might not be that big.
Yeah, I get that. But
Examples escape me, unfortunately.
Between the t value and the p value.
Yeah.
Yeah.
The higher the t value, the lower the p value.
Yeah.
Conditional on the degrees of freedom.
Yeah.
Yeah. Okay, so that's the other 2 t statistics that I skipped over. Kind of made sense to skip over it actually.
So, sorry, but why is the p-value lower but the t-value is higher?
Because of what the t-value represents. The t-value, why is the p-value lower when the t-value is higher? By design, by definition, actually. So what you're doing, what the p-value means is the area under the curve from the t-value and out into infinity. So remember that these curves get really skinny at the end. So as the t-value, because the t-value is sort of centered on 0, as the t-value gets big in plus or big in minus, the curve goes and dips down like this, and the area under the curve gets less and less and less and less and less and less. So it's by definition, actually, it's analytically true. Yeah. because the p-value just means the area under the curve for the t-value off into infinity. Okay? Okay, so let's go back to the exercise and look at some mess data, slightly more messy data. So what we're going to do first is download, or install rather, another package, another data package. And this package is the fuel economy package, and this is a package that was made by the EPA. So don't trust, and it's based on measurements of fuel efficiency for different kinds of cars with different variables in them. So take the diesel statistics with a grain of salt, I guess, particularly for VW. Otherwise, it's a nice data set because it's messy and it's complicated and it's real. So what you need to do first is install it. So run that line of code. I've already installed it, so I won't run it. And then load it up in your library. And I get a warning because my version of R is older than yours. Okay, and then load up. So what I'm going to do now is I'm going to clear my workspace using the broom because I'm not going to look at the height data anymore. And then I'm going to load up the data, and the specific data set that I want is the vehicles data set. So this is a complex data set. It's got lots of stuff in it, and I can show you that now this head trick will come into its own. Now you'll see why we need something like this. So what we've got here is 33,442 observations with 12 variables. So if we wanted to see what sort of data that was, and we just wrote vehicles, we get such a long set of data that we actually can't get to the top.
How did you do that?
Sorry?
How did you get this?
How do I get the data? Just type in vehicles, because vehicles is an object.
In the console, not
Yeah. I'm just demonstrating stuff. Yeah. So typing vehicles is not so useful because you have to scroll all the way to the top and it's very disorganized. So that's why this head thing becomes useful. And we can look at what sort of data is in that data set. So what are these variables in this data set? You can see you've got an ID number, which is just a number for a specific type of car. The make is this AM General. The model is DJ Po whatever. Two-wheel drive. The year that it was out is 1984. And right, this is where you'd have like Toyota Hilux, or makes Toyota, Hilux is a model, Skoda Octavia, make, model. The class, which you can have different sorts of cars. The transmission, how many gears has it got? You don't have to know all this, I'm just saying the sort of information that's in this.
Does data always look that nice?
This is very, very nicely sorted data made available by the EPA. How the drivetrain of the car, 4-wheel drive, 2-wheel drive, how many cylinders it's got, the displacement of the cylinders, so how big are the cylinders, what sort of fuel it uses, and these are the ones we're going to be interested in, is the, not so much the highway, but the highway fuel efficiency, and this is miles per gallon because it's American, and the city efficiency, so this is also miles per gallon for driving around in the city. So I said my brother's a mechanic in the mines. First thing I do is I look up a car data set. So we can now sit down and decide to pose ourselves a question about this data set. So we need to set ourselves a task. So let's set ourselves a task of comparing the city fuel economy of, say, all the mid-sized cars for two different car brands. We might do this if we want to buy a car.
Comparing, could you say it again, comparing
The city fuel economy. So how many miles per gallon can you get out of two different kinds of all the sorts of models, mid-sized models of two different kinds of car. So let's make it VW and Audi.
And what? And BW and?
Audi. So we're looking at VWs and Audis. So let's make a data frame that's only got the data that we're interested in, because this has got a lot of data that we don't care about. So what you're learning about here is sort of selecting and picking out data that's relevant for what you want to do. Okay? And there's a number of different ways to do this, and I'll show you a more efficient way as we go along, but for now we'll keep using indexing because it's working and it's reinforcing this concept of indexing. So let's make Audi midsize. Okay. Oh, actually, no, we're not going to use indexing. I'm going to teach you the new concept now. And it's a good concept. It's very useful for these sort of messy data sets. It's very useful. It's more efficient than writing lots and lots of index, $, and so on. It's a function called subset. So what does subset do? Subset's a function, so it takes an input. And the inputs that it takes are data frames and conditions. And you can think of these conditions as indexes, as stuff that's picking out and pointing to things that you're interested in. So the first thing we have to put in subset, actually I just had a thought, this could also use tilde. Let me just try something, you don't have to do this. I bet you it'll work. No, it wouldn't work. I was going to see if it will work with tilde notation, but it won't. No, so, okay. So subset, the first thing we put is our data frame. Trying to keep everything super, super consistent. Is our data frame that we're interested in, which is vehicles, and the conditions that we want to look at. And those conditions are the make. We're making the Audi data frame, or the Audi array, sorry. So we want the make to be equal to Audi. And we want the class, because we're interested in mid-size cars only, to be equal to mid-size cars. So how did I know that that's what the class was labeled as I looked, basically. You have to go in and look. So you have to know your data and you have to play around with your data. So let's see if that works. So that'll give us a new array of 772 objects. Or observations, sorry. So now we've got an array that's just those rows in this big data file that correspond to Audi in the make column and midsize in the class column. So if we look at that, it should have the same headings, but it should only have Audis that are mid-size.
Is that a space for?
No columns and 72 rows, so I'm making a mistake somewhere. Oh, sorry. And So we don't want a comma there, we want an and sign there, because we're interested in stuff that's both got make, Audi, and class midsize. So that's a logical expression. And now we've got 12 variables with 157 observations, or 157 cars. So we should have 12 columns and 157 rows.
And if we don't?
Something's gone wrong. Or something's gone wrong for one of us. It could also be me.
I get the same issue.
Okay.
Can you show the entire line?
And did it something went wrong?
You must not put it one because the cars with okay.
So subset function, input vehicles for one argument. Input make equals to Audi and class equals to midsize cars is your other argument. Yeah, it has to be double equations because that's the things that already exist equals. And so if we look at the headings, we get the same headings: ID, make, model, year, class, transmission, and so on. The make is all Audis, the class is all mid-sized cars. So that's good. We feel comfortable. So we can do the same thing with VW. And we just have to change that to Volkswagen. And again, make's always Volkswagen, class is always mid-sized cars, so we're happy. Okay? So we want to make a data frame that has both of these together. Can anybody remember which function we used to put the two together? Sorry? There's 100 different ways to do it. Data.frame is going to work just fine. So data.frame, Audi midsize, comma, VW midsize. There's one called rbind that was also work. I think it's rbind or cbind. I always get those two confused. Or I think C would also work in concatenate. Concatenate work with data frames? Sorry?
Only vectors list, I guess.
Doesn't work with data frames. Okay, so
Yesterday we only used it.
yeah, we can try it. So let's try it. I'll just try it in my console because I expect that it won't work. No, it puts it in a list. We don't want it in a list. So C doesn't work here. So to make this a data frame, we use the data frame function. So let's call it midsize, cars, data.frame, which means put things in a data frame. I think this would work. If this doesn't work, I'll use rbind. Differing numbers of rows. It's trying to put it next to it. So let's use rbind. Okay, and then I'll explain what that does. Okay. So these are different ways. There's lots of different ways of putting data frames together and pulling data frames apart and putting them back together, and lots of different ways of pulling vectors apart and putting them back together. And this one that we're using is one called rbind. And what rbind means is bind by row. Bind just means stick. So stick this data frame on the bottom of this data frame by putting it under the rows. If you used cbind, that would be column bind, and it will put it next to it. So you'd have all of your Audi data and all of your VW data. What rbind does is it respects the rows that we've got so that our variables stay the same.
And what was the second one?
Cbind, which means column bind. And I always get them mixed up because it's not intuitive to me and I always get it reversed. But if we look at this, we should hope to only see the same variables as before, and I think we will. And we do. So now we'll have all the Audis on top and all the VWs down the bottom, and we'll still have a data frame. So now we've got a little reduced data frame that we can use to do our specific analysis on. Okay? So we can do a t-test. So we can now see whether Audi or VW is more efficient for city driving. Let's do that. Let's use the same notation. City, fuel efficiency. We're missing as a function of, no, that'll work, as a function of make. And the data we want to use is mid-size cars. Okay, so we've done a two-sample t-test, independent samples t-test, like we described in the theory bit.
Could you scroll down a bit?
Oh, sorry.
Thank you.
And don't highlight. That was the other thing. So here we've used the tilde notation again. City as a function of make in the data frame mid-size cars. So what have we learned based on our analysis of the real EPA data?
Average fuel efficiency.
Is,
Well, it's a smaller number.
yeah?
You use less fuel.
Yes, it is.
So that would
I'm
be-
getting tired. I interpreted it wrong. Yeah, Audi's more fuel efficient in the city. And if we want, we can check for what it's like on the highway. So okay, fair enough. I should get an Audi. I should invest extra in an Audi because they're more fuel efficient. But actually, I commute. So maybe I should get a VW. Let's have a look. No, should still get an Audi. Actually, no, I was right. It's more fuel efficient is longer. It can go more miles per gallon. Yeah. So actually you should get a VW in both cases because the VW's got a higher miles per gallon. Okay, so if you've got a VW, you'll be able to go nearly 20 miles per gallon. If you've got an Audi, you'll only be able to go 6 miles per gallon. So with all of the 16 miles per gallon. Don't want to get sued. This is going on YouTube to keep accurate. Just from this alone, you should buy a VW and save your money, unless you want the badge. Okay.
So what does the t-test tell us?
Sorry?
So the t-test tells us what?
T-test tells us that the difference, so if we go to this one, the mean city fuel efficiency of a Volkswagen is about 20 miles per gallon, and the mean for an Audi is about 16.2 miles per gallon, 16.3 miles per gallon. The degrees of freedom is based on how many cars we've got in our sample. The T statistic is this difference punished by how much variability there is in the samples.
What is that? No, that's low. No, that's high.
That's high. And if we were to plot this T statistic on a T distribution, it'd be so far off in the tails that there'd be very, very little area under the curve.
So you cannot rely on this.
You can rely on this because it's a very low p-value. It's an insanely low p-value. So it's very unlikely that the null hypothesis is true. And it's the same for
That was what you said, that high t-value equals
low p-value. Yeah.
But I still don't get the degree of freedom.
Don't worry about the degrees of freedom.
Don't worry about the freedom.
You can come back to degrees of freedom. It's an important concept, but I think it's not the most essential one at the moment. Okay, so if we just had that, we would say, all right, I'm not going to invest in a badge. I'm going to save money and buy a VW. Technical stuff, Anya?
Yeah, it's just
Help?
Josh,
Yeah.
would it make a difference if you specify the one-tailed test here? We are only interested in one direction.
Yeah, so this is checking in two directions. That'd be a one-tailed test would be a bad model here, because you don't know in advance whether an Audi is better than a VW. You're interested in both outcomes. So this is a case where a two-tailed test is actually really suitable. And I think the default for this function is a two-tailed test. So if you want to turn it into a one-tailed test, you have to go in and change that. But I might show that. Yeah? Yes, that's the next step. Yeah. Okay. So moving on. Let's look at now if this is the best way to look at model our data. If just looking at these two makes is sufficient, or if there could be something getting in the way of our inference. So how do we do that? Well, we can start to do that by visualizing things and looking at our data. So let's plot our data. So let's just focus on city fuel efficiency to keep things simple. And let's plot a histogram of the Audi data.
Now you're writing cities, but you have that I in there?
Thank you. Okay, so we're pointing only to the Audis, and we're only interested in the city column, and this is green because we're interested in an item within an array, not an object. So this has got the quotes. And we want to feed this line of numbers into our histogram function, which will then produce a plot. And so that it doesn't crash, I'll make my window a bit bigger. And let's see what the Audis look like. Right? There's something going on in the tails there. If you look, there's a little cluster on the end that could end up being important. So let's note that. And then plot the VW. I'm getting the problem that somebody else got. It could be because it's not VW, it's Volkswagen. Again, there's something going on in the tails. that matters, that could have an influence on our inference. Okay, so we want to look at this. We want to start to be able to compare these two plots that have got something, both got something going on in the tails, and we want to know how much this something going on in the tails might matter. And I think, like I said before, that the histograms might not be the best way to do it, again, because you have to keep flicking back and forth. And so probability densities might be a better way to look at it. So let's do probability densities like we did before. This also allows us to practice concepts and the coding for this. So let's look at make a new variable called Audi density. And that's the density of the Audi, what have I called it? Trying to stay consistent. It's mid-sized cars. Cut from here. Cut and paste this line, same thing. Let's do VW density. Let's evaluate both of those. And then plot them in the same way that we did before. But we want to do that cull trick again, because that was nice. It gave us those alpha values, right? We could make the graphs a little bit see-through. So I want to take the gold color and the dark green color. What's going on here? Oh, I was missing that. And we want to adjust their alpha. Right, so that makes me a new color, new set of colors. Could not find function adjust because it's no function adjust, it's adjust cull. Adjust color. Now we're ready to plot. So let's plot just one of them. It doesn't really matter which one we plot. So we just go Audi first. And already, because I've looked at this, I know we're going to have that problem of the axis. The two distributions are going to have different axes, so we need to fix the boundaries of our x-axis so that we can see both distributions. We're going to have to do that in advance, just like we ended up having to do that before. So we do that with this x-lim, limits on the limits on the x-axis, 10 and 40. And then plot. And that gives us a distribution, probability distribution for that city fuel efficiency. So how many miles per gallon you can get for an Audi. And the probability of each of these values. Not taking any of the other variables into account. So averaging over the year that the car was made, how many cylinders it's got, the displacement of its pistons, all sorts of things like that. So how big the engine is, all sorts of things like that. Whether or not it's a hybrid. And then let's add our polygons.
Can I just get a second to catch up?
Sorry?
You're going too fast.
Yeah, everyone was quiet. That's why I thought. It's when I hear talking that I slow down.
Thank you.
Okay, that's my signal that I use.
On your y-axis on the chart, the density, the 0.50, 0.30, what are those points actually? How will you calculate them?
That's the values that you would need for the probability to give the curve under the area under the curve equal to 1. So that's the p, that's the probability of each infinitesimally small value. So if you've got really wide axis, you'll have a low p. Right? So if your variable goes from 0 to 1,000, and you've got a distribution that sort of covers all of that area, you're going to have to stretch it out and squish it down quite a lot. And that's like if you've got a two-sided coin, the probability of any given side is going to be 0.5, 50% of getting a 1 or a 2. If you've got a dice with 6 sides on it, the probability of getting a 1 would be 0.16, because you've got 5 other kinds of events that could also occur.
Oh, maybe it needs.
Make the window bigger.
Yeah.
We only use an alpha of just 0.5, I think. You've made them very transparent on it.
Yeah, you could just make what looks nice.
Sure.
Yeah.
This is very transparent.
This is very transparent. Yeah. You could just make a few different things and try printing it up and putting it in different contexts.
Oh, the missing something.
Play around with it. Okay?
Just a second.
So I'll slowly go on. No, it's good.
What was that?
Density just means probability of a given value. So here, density at 15 is the probability of getting exactly sort of 15 miles per gallon. And that's about 0.15. Probability of getting 20 miles per gallon is a lot lower. Okay. So I'll go on and put polygons on, which is what we did before. So that'll just colour in that one. Oh, 0.05. Now I see what you mean by low alpha. Give it a little bit more colour. I thought I put 0.5. So this variable here, or this argument here, if you change this number, you'll change how dark it is. The lower number is less dark. Then make the other polygon, which is the VW density. And that will be the second colour, which is our green. And that looks like that. So this is an okay model of the data, right? It's okay. But it's not perfect because there's a clump on the end of the distribution. And so ideally, we shouldn't have done any statistical tests here. Because now we've done a statistical test, we are increasing the risk of finding an effect that doesn't really exist. We're increasing the risk of rejecting the null hypothesis when we shouldn't, whenever we conduct another statistical test. But we can correct for that. And the way that we can correct for that is we punish ourselves. So what we're going to do is we're going to say we're going to accept an error rate based on a p-value significance level of 5%. But we're going to do that across all of the tests that we run. So that means we're now allowed to run 20 tests, but then we have to add all of our p-values up from those 20 tests, and they have to be under 0.05. Or another way of putting it is, for every time we do a test, we divide the p-value by the number of tests that we do. Okay? So rather than accepting 0.05 now, to get a statistically significant result for any further tests we do, we have to divide by 0.025, which is harder to do, And then we can conduct multiple tests of the same data set without breaking the rules of the logic of null hypothesis significance testing. Does that make sense? Okay.
If it's the same test, or
If it's the same data set.
but different kinds of
tests, yeah. Just very, very strictly speaking, if we then go and run a regression or an ANOVA, we use a different model, then we have to correct the p-value that we accept as significant by the number of tests that we do. And that's called a family-wise error correction or a Bonferroni correction. They're the words. So if you ever hear Bonferroni corrected, that's what it means.
Say that again?
Bonferroni corrected. That's the guy that came up. His name was Bonferroni. Another way, you can also call it the family-wise error, which is because you've got a family of tests that you're running. Now this is a very difficult philosophical topic again, because what constitutes family? If I collect new data, does that mean I've necessarily I can start from scratch? Should I correct can it be interpreted so strictly to mean that for my life as a person, I have to correct for every single test I do? And there's no objective boundaries for what constitutes something that fits within that family of things that have to be corrected for. So if I write a new paper with the same data set, does that mean I then need to go back and retract the earlier paper that's been published, because now P0.05 is no longer my significance level, now 0.025 is, and I found 0.03. So it's not a good solution, but it's a solution. It still involves a lot of social stuff that's not counted.
Is it because some of the values are depending on test yield?
No, it's because you're willing to take the risk. You're saying when you set your p-value, acceptable p-value of 0.05, you're saying I'll take the risk that 1 in 20 times I'll reject a null hypothesis that was actually true. And if you want to keep that criterion, 1 in 20, then every time you do a new test, you have to reduce that criterion.
Couldn't you just then do it the test 100 times and then take the average?
Well, then you'd have a p-value. If you did 100, your p-value that you would need to pass to accept a null hypothesis as being false, to reject a null hypothesis, would be 0.0005, because you have to divide it by 100.
Is it because then you've done one of the 20?
Yeah, then you've done one of
the
yeah,
20,
exactly.
and the third of the 20, then
And you
have
want to
to
keep it.
adjust the
You want to keep it 1 in 20. Okay. So what we're going to do, we have a very quick 5-minute break, and we'll come back and do one more thing with this data set, and that is do another test where we look at what's happening in the tails. Yeah?
Is it okay with the question?
Yes.
I'm just using overview now. The graph on the right now, does that show the probability of, for example, a Volkswagen car driving that many miles per gallon?
Yes. Everything else, so we're ignoring everything else in the data that we've got and saying what's the probability that a generic Volkswagen car could have been made in the 60s. It could have an engine size of whatever, could make 30 miles per gallon. It's very low.
So it's the probability of the
Yeah,
solution.
of any randomly selected Volkswagen car, ignoring every other factor. Yeah?
Why is it, I don't know if that's a statistical or a mechanic question, but why is it more likely to drive 30 miles per gallon than...
That's what we're going to look at.
Couldn't it be software,
like maybe shop because we have all sort of, so it could be a
Yeah.
specific niche that
okay, like
we
an
do
eco
because
business.
all
It's going to be some other factor.
Oh,
Yeah, but it's 3:30, so can we come back at 22 and continue? Good.
Yeah, we can also do that.
Sorry, 3:34, so come back at 22.